Hello, calculus fans. Okay, so I would suggest that you look at the bottom of page 335, starting with figure 10, and then continuing through to the bottom of page 336. This puts all the ideas together of computing the area under a curve using approximating rectangles. So just to hit some of the highlights, if we're going to compute the area under the curve y equals f of x over the interval a to b, we divide the interval into n equal size subintervals of width delta x equals b minus a over n. So the length of the whole interval is b minus a, and we're chopping that up in n pieces, and so that's how we get b minus a over n. So we call that delta x. So then when we chop up that interval, we're going to have partition points, and they look like this. Now the left endpoint is A, and the right endpoint is B, because we're starting with the interval from A to B. And then to move over to the next partition point, we're just going to add delta x. And then we keep adding delta x as we go until we get to B. Now let's say we're going to compute R sub n. Now that's a right-hand sum. So the right-hand endpoints of the subintervals are going to be x1, x2, x3, all the way up to xn. You notice that the first subinterval goes from x0 to x1, so the right-hand endpoint of that subinterval is x1. Then we get the heights of the rectangles by plugging in those values into the function f. So these values here, these are going to be the heights of our rectangles. All right, so now we can put together R sub n. R sub n is going to be the areas of all these rectangles. Now these are the heights, and the widths are all delta x. So here's our expression for what R sub n is. This is the sum of the areas of the rectangles. And if we take a limit as n goes to infinity, at least this is going to appear to approach the actual value of the function. That's at least the idea of what we're dealing with. All right, that's going to lead us to make a definition about area. We're going to define the area of a region that lies under the graph of a continuous function f of x. It's going to be the limit of the sums of the areas of the approximating rectangles. So limit as n approaches infinity of R sub n, which is just the limit of this thing right here. So as n goes to infinity, we have more and more of these approximating rectangles whose areas we add up. Now I'm going to give you a couple of facts about this definition. These are fairly useful and important, but we're not going to prove them. The first fact is that as long as f of x is continuous, this function will always exist. Now here's the real interesting fact. If we replace R sub n with L sub n, this limit still exists, and it's going to give us the same value. So it's kind of interesting. It doesn't matter if you choose right endpoints or left endpoints. The limit still exists, and you get the same thing. You can choose left or right approximating rectangles. But the situation is even more interesting than that. So when we make R sub n or L sub n, we're choosing the right or the left endpoints of the subinterval at which to evaluate the function. It turns out that if you want to choose any point in the subinterval to plug into the function to figure out the height of the rectangle, you actually can still get the same limit, and it won't matter. Now here's another bit of notation. You can actually use what's called sigma notation to write sums more compactly. And so this right here is a compact way of writing this sum. So the sigma tells you that we're going to add up all of these things where k ranges from 1 to n. So anytime you see this sigma notation here, you have to know that you're adding up n things because you're starting at k equals 1 and ending at n. Now, let's just give a specific example. You remember that we had these explicit formulas for summing the sum of the first 10 integers or squares or cubes, and then we had nice formulas for this. We can actually rewrite this using sigma notation. And if we do that, then this is what we get. Okay, that's all for now.